Okay, so welcome to the last PA section. So we're gonna cover seven questions for today, and they're all about the energy equation and the what's it called, the impulse and momentum balance. So we have 7 questions, but I think compared to like the question from 2 weeks ago, the math's gonna be easier. So let's. Okay, so let's start from the first one. So oops, it's kind of like a pulley question, but like now we're going to calculate the power. So we have like a 1,000-pound elevator, and there's a motor like on here. So the motor is kind of pulling the elevator or the box on here, like pulling up. So on here it says the motor exerts a constant force of 500 pounds on the cable. So that means on the cable, like this one gonna be 500 pounds. And on each section of the cable, they're all gonna be 500 pounds. And also on here, 500 pounds. And we have the efficiency of the motor, and we're going to ask what's gonna be the power of the motor when the displacement of the elevator is 15 feet. So let's first take a look at the equation for the power. So power is equal to the force times the velocity. So that is about the linear power. And like maybe like in the future, you're gonna see the power is also gonna be equal to m times omega. So it's gonna be equal to the moments times the angular velocity. So that is the equation for the power, like in the mechanical sides. And like in the electrical sides, you may also notice power is equal to like current times the voltage. That's something else. We don't need to worry about that now. So like we're gonna basically using this equation to find out the power. So like from this equation, we can see we have two parameters need to be like determined. The first one is the force, and the second one is the velocity. So we are going to find out what's gonna be the force on the motor and what's gonna be the velocity, like on the rope, when S is equal to 15 feet. So the force is obvious. It's like it's given. It's already given. It's 500 pounds. So the only thing we need to find out is the velocity. So first we can do a free body diagram of the elevator. Like now we're looking for the velocity. So when we are drawing a free body diagram, it's going to be like this. There's a weight of the elevator that is 1,000 pounds. And on the right side, there's a lifting force, 500 pounds. And like on here, there's actually two 500 pounds. And here's also 500 pounds. So we have all the force that we need to calculate the acceleration. So this one is the free body diagram. So first step, we can, from the free body diagram, can use the Newton's second law. So that is the force in the y direction is equal to m times a. So the force, the resultant force in the horizontal direction is just 3 times 500, like the force from the cable, minus the weight of the elevator. Is equal to m times the acceleration. So the mass is 1,000 pounds over 32.2. Like remember, this one gonna give us slug, which is the mass unit that we need to use like when we're dealing with the empirical units, times the acceleration. So like from this equation, we can easily find out what's going to be the acceleration. Like everything unknown, we just need to looking for the acceleration. And the result is 16.1 feet per second square. So now we have the acceleration and we're looking for the velocity. So like remember, we have an equation that is Vt square, like the final velocity square root of the power of the final velocity minus initial velocity to the power of 2 is equal to 2 times the acceleration times the displacement. So in this equation, like we know at the very beginning, the elevator is starting from the rest. So that means this one goes to 0. And Vt is the unknown we're looking for. So 2 times acceleration, we already found it, 16.1 times the displacement. So the displacement is s equal to 15. So times 15. So that is the displacement, and this one is the acceleration. So from here, we can find out the final velocity of the elevator is equal to 21.98 feet per second. And also, like, keep in mind, this velocity is the velocity of the elevator. So it's the velocity of this box. I'm gonna write it here. So now we find out the velocity of the elevator. But what we need in the equation, in the power equation, is the velocity of the cable. So now the question becomes, we know the velocity of the elevator, and we need to find out what's gonna be the velocity of the cable, like what's gonna be the velocity on here. So everything gonna be back to our pulley and cable question. So the first one is we find out the velocity of the elevator, and second step is we're going to find the velocity of the rope. Okay, so like before, what I like to do is kind of like simplify this system. So the system is kind of be like we have a pulley here and a rope here and a rope going up. And then we're looking for we're going to find out what's going to be the velocity on this point. So like I personally like to kind of like put a dummy box over here. And then like everything is connected to the elevator. Well, shouldn't be solid. So yes, something like this. Can I make it bigger? And then we're gonna pick a reference point. So like usually what we do for picking the reference point is we want to pick a point that is not moving at all. So it's like for this system, maybe we can look at this. If we're picking like somewhere like over here, like when the elevator is going up, the location of this one is actually like kind of going up. So like the good practice is we pick a point that is never going to move. So like, why don't we pick this one? So like for now, I'm gonna pick this pulley as the reference point. So gonna be like this. And then I'll say like going all the way down is SB and going to the motor or the point we choose is SA. And then just like before, we are going to say the total length of the rope from here go all the way to here. It's a constant, and that is equal to going up, so that is 1 SB. Going down, the second SB. Going up until this point, it's another SB. And the last segment from here to here is a SA. And then like just simplify everything, we have 3 times SB plus SA. And then like, remember the equation, like in the first 2 P section, we always like to use is velocity is equal to ds over dt. So we are going to we're gonna derive the whole equation. So the derivative of the L or the length of the rope is 0. And like before, that is because the L is a constant. Can you use black? And that is equal to 3 times VB. And well, actually on here, like we noticed that if we're only talking about the displacement, that is like it's it's not a vector, but like when we're dealing with the velocity, that is gonna be kind of like a vector. So like on here, the SA is actually going to the other direction. So we should put a negative sign here. Means like the direction is gonna be different from the VB. So here we have the equation, and then we can easily say 3 times VB is equal to VA. Okay, so now we find the relationship between the elevator and the rope. So the velocity of the rope is equal to 3 times VB. That is the velocity of the elevator. That is 3 times VT. So it's going to be 3 times 21.98. And okay, I didn't calculate that. Just find the calculator. 3 times 21.98. That is 65.94 feet per second. Okay, we find out the velocity now. And the last step is just to calculate the power. So now first we need to calculate the power from like the output power from the motor. And that is just the equation from like above. P out, I should say, is equal to F times VB, VA. So which is 500 times velocity we just got 65.94, and the result will be 32.97 times 10 to the third pound-feet per second. So here's the output power, but what we need is the input power. So on the question on here, like the efficiency of the motor is given. So the efficiency is essentially equal to the output power over the input power. So from here, we can get the input power, and that is just output power over the efficiency. And that is 32.97 times 10 to the third over 0.65. And that is equal to 50.72 times 10 to the third pound feet per second. So here, here's the final answer. So maybe in the final exam, he's gonna ask the units in horsepower, and in that case, he should give you the conversion formula. So to convert the pound feet per second to the horsepower, we just need to use this number divided by 550, and essentially going to be 92 horsepower. It's just because this power unit is something not that usual to see in the daily life, I guess. Okay, so that is the first question. So for the first question, you just need to know this equation. The power is equal to force times velocity. And then from the free body diagram, you find out the acceleration. Then from the acceleration, you find out the velocity for the elevator. And then use the relationship of the cable and the pulley, you'll find out the velocity for the motor. And then you find out the power, and then translate, convert it to the horsepower. That's it. Okay, then we go to the second one. So the second one is actually a energy, conservation of energy question. So we have a 5 kilogram collar. That is this one. That is 5 kilogram. Has a velocity of 5 meters per second when it's at point A. So that means VA is equal to 5 meters per second. And it's gonna travel down the smooth guide, so the smooth tube here. And we're going to find out the speed of this one when it reach point B. And there's another spring attached to the collar here. So we know the unstretched length of the spring is 100 millimeter. And also we know the K, the coefficient for the spring is 50 Newton per meter. So we're just gonna use the energy balance. So the energy at the location 8, or the energy at the, how should I say that? The energy of the entire system when the collar is at point A is equal to the energy of the entire system when the collar is at point B. So it's EA is equal to EB. And then the energy in all our the equation, the question in our class is they're all gonna be the kinetic energy plus the potential energy. On the left-hand side is the same. So we're talking about the kinetic energy of the entire system and the potential energy of the entire system. So on the left-hand side of the equation, the kinetic energy is the only thing that is moving is the collar. So gonna be half m VA squared, and the mass gonna be the mass of the collar. Plus the potential energy. So when the collar is at this location, there is a potential energy from the height. So it's mgr plus the potential energy from the spring. So that is half k x squared, and this x, like the x over here, will be the length of the spring. So here will be the length of the spring when the collar is at 0.8 is going to be 0.2 to the power of 2 plus 0.2 to the power of 2 square roots of this one minus the original length of the spring, that is 100 millimeters. So it's 0.1 meter to the power of 2 is equal to like the energy when the collar is at point B. So that is going to be a half mvb squared plus, we don't have the potential energy from the height now, so it's plus 0 plus the potential energy from the spring. So it's half k, and that is going to be 0.4 minus 0.1 to the power of 2. And then from this equation, like the only unknown is the VB. So like everything is the known condition. I'm just gonna write down what is this. So this one, like square root of 0.2 to the power of 2 plus 0.2 to the power of 2 is the total length of the spring. And the 0.1 here is the original length of the spring. So the equation inside this bracket will be the stretched this of the spring. So as long as you can build up this energy balance equation, like everything left will be just the mass, like looking for VB. So now I'm just gonna plug in the number into the equation. So half mVA squared, mass is 5 kilogram, and the velocity is 5 meters per second, times the, plus the mass is 5 times the gravitational acceleration 9.81 plus the height. So the height is over here, and that is 0.2 meter. Oh, another thing is like we're doing something like in the SI units, you always want to change like all the units to meter, Newton, and kilogram, and then do the calculation. Okay, and plus half k is 50, and that is just numbers there. Minus 0.1 to the power of 2 is equal to half. Mass is 5 kilogram times VB to the power of 2 is the unknown, plus 0 plus half times 50 times 0.2 plus 0.2 minus 0.1. So again, this one is also calculating the stretch the length of the rope. Okay, so we can do this. And then we have a very long equation here. Like it's just long, it's not difficult to calculate. So I'm just gonna give out the final answer for VB, that is over here, this value, which is equal to 5.33 meter per second. So now, like you can see, for most of the energy balance or the impulse momentum balance question, like as long as you understand what the question is talking about, like usually you only gonna have like one very long equation, and the math is not gonna be that terrible. Then like you just need to pay attention when you're actually doing the calculation, like for those values, then you should be able to get the correct result. Or like I remember when I was doing those questions like in first year, I usually like I always got those equation correct, but like I always made mistake when I like actually do the math. And even in that case, you won't lose like a lot of mark. So it should be fine. So that is the second question. And the third one. So the third one, like there are actually gonna be two ways to solve that. The first one is, well, actually the idea is the same, but like the way we express the energy balance equation gonna be a little bit different. And so like usually, like as before, I like to use the energy at state 1 is equal to the energy at state 2. But like in this case, there's another way. It's gonna be the kinetic energy at the first place plus the work done by the external force from 1 to 2 is equal to the kinetic energy at the second state. So like these two equations, they're actually the same. Like you're just gonna like the order of the equation gonna be a little bit different. So let's read the question together. So we have 3 kilogram package. 1, 2, 3, 4. It's held in place by friction. So that means when you put those blocks on there, like it's not gonna slide. It's not gonna slide through the cable or the belt. It's not gonna like slide down. So it's gonna be like fixed in this location. And also like the belt is disengaged from the drive motor. Means like the motor is not moving, like the belt is just gonna move itself like by the potential energy. And the system is gonna be released from the rest. So it's like we place those four boxes there, and then the system gonna like start to move because like the box gonna trying to drop down from the rest. And we're going to find out the velocity of the package 2 when the velocity of package 2 when they leave the belt at point A. And like this is the direction of the motion. And we're going to find the velocity of package 3 when they leave the location A. So first, oops. Let's try to use this energy equation for the first question. So what is T1 at the very beginning is like, we know the system is released from the rest. So that means the kinetic energy at the beginning is 0 plus this one means the kinetic 0 plus the work done by the external force. So in this case, like the only external force is the gravity. Like for each box, there is going to be a gravity acting on those boxes. So since we're analyzing the whole system, so like we're going to have 3 boxes. So it's 3 times the gravity, that is mg, times the h. So like when the second box slide down to the first location to here, the horizontal direction, like from gonna say from here to here. So it's like the horizontal displacement is going to be equal to 2.4 over 3 divided by 3. 2.4 divided by 3. So this one is the horizontal displacement for each box is equal to the kinetic energy, like when box 2 arrive the location of box 1, the kinetic energy is also going to be for 3 boxes. So we're going to have 3 boxes over here. So it's going to be 3 times half mv squared. Okay, then we can plug in the value. Can I make this one smaller? So will be 0 plus 3 times the mass. The mass is 3 times gravitational acceleration is 9.81 times the height 2.4 over 3, that is 0.8. Is equal to 3 over 2 times the mass is 3 times the velocity, which is the unknown. And then just like some mass calculation, then you will be able to find out the velocity is equal to 3.96 meter per second. So that means the velocity of both 2, 3, and 4 box at this moment is going to be same. It's going to be equal to 3.96 meter per second. And then let's calculate the second part. So the second part is looking for the velocity of the box when the package 3, when the package 3 is at the location of is at A. So we're going to do the same thing as like T2 prime plus U, the work done by the external force from the second state to the third state is equal to the kinetic energy at the third state. So the kinetic energy at the beginning of this question is going to be a little bit different than before. Like before it's 0 since like everything's like starting from the rest. But now we have a velocity. We already have a velocity here. And like we like at this moment, there's only 2 boxes on the belt, because like box 1 is already fall over, and box 2 is also already like dropped down. So we only like at this moment we only have box 3 and box 4 still on the system, like still inside the system. So like for T2, we only need to include the kinetic energy for box 3 and 4. So that would be 2 times the kinetic energy of box 3 and 4, half times n times v squared. I'm gonna call this one VA. And the meaning of this equation is only 2 boxes remain on the belt. And the work done by the external force is going to be same as before. But now, like, since we only have 2 boxes, so it's going to be 2 times the gravity times the height. And they're equal to the same thing, 2 times half mv p squared. So on the left hand side, like we're just gonna plug in the number. So that is 5 times 3.96 to the power of 2 plus 2 times 5 times 9.81 times 0.8 is equal to 5 times VB squared. So like now in this case, we can find out the value for VB. So that is equal to 5.649 meter per second. Like up to this point, we're just going to like just simply solve the math to find out the value for VB. Can I mark it down? So the 3 here means there are 3 boxes on belt. Yeah, so that is the 3rd question. And like, there's another way to solve that. It's a little bit more complicated, like it's a little bit more math to do by comparing using this equation. Because the good thing about this equation is like, we are only considering the external force. I mean, the work done by the external force. So another way to do that is like, before we are just saying the energy at the first moment is equal to the energy at the second moment. So it's like the energy at the very beginning is equal to the energy when like box 1 dropped and box 2, box 3, and box 4 arrived those locations. So like it's going to be the same, the kinetic energy plus the potential energy, go to the kinetic energy plus the potential energy. And at the very beginning, the kinetic energy is going to be 0. The potential energy, like However, you need to calculate the potential energy for 2, 3, and 4 balls. Like if we're saying the ground or the reference point or the datum is over here. If we're saying the datum is here, like for box 2, that would be plus M2 G2 H2 plus M3 G3 H3 plus M4 G4 H4 is equal to the kinetic energy of 3 boxes, going to be 3 times half mv a square plus the potential energy is going to be the same things like M2 G2 H2 prime, like H2 prime, like H2 now is going to be different from the H2 before, plus M3 G3 H3 prime plus M4 G4 H4 prime. So like just gonna plug in a number and like do all those like very long equation. So essentially it's gonna be the same since like we know the H2, this H2 gonna be equal to H3 prime and H4 prime gonna be equal to H3. So this term and this term gonna be canceled out. So like eventually you're gonna see the same number, like same equation and also the same result, but just like longer equation. Like using this rule is gonna be like the equation gonna be shorter. Oops. Okay, so the fourth one, there. So again, just another energy balance equation. Like we're all dealing with the energy balance equation today. So when S is equal to 0, the spring like on here is unstretched. And so that means the original length of the spring, like the spring gonna start from the rest. And we're now gonna put the spring back for 100 millimeter and then release. So that means we're going to have some kinetic energy stored in the spring at the very beginning. So the mass of the ball is 0.3 kilogram. This one is 0.3 kilogram. And we're going to calculate the speed of this ball when they reach this location, like on here, when the theta is equal to 60 degree. And theta is equal to 60 degree. And also like the surface of the, like all the surface gonna be smooth. So that means we don't need to consider any friction loss. Oh yeah. So we need to calculate the speed and also the normal reaction. Like we need to calculate the speed and the force, like exerting from the ball here. So first one, we can do a free body diagram of the ball. So it's gonna have a gravity, and then like it's gonna have like a reaction force from the from whatever this is, like from the rail. It's gonna be normal to the surface, the reaction force. And also we know this angle gonna be 60 degree. So that is the free body diagram. So first for the velocity or for the speeds, we're just using the energy balance again. So like the energy balance at the first moment is equal to the energy at the second moment. Moving everything to here. So kinetic energy at the first moment plus the potential energy at the first moment is equal to the kinetic energy at the second moment plus the potential energy at the second moment. And the kinetic energy at the first moment, like everything is it's not moving, so that is going to be 0. So this one is 0 plus the potential energy. So the only potential energy you have is the potential energy in the spring. So that is half kx squared. This is the energy in the spring. And also, like, remember when you're actually doing the calculation, the x over here is the stretched length. Oops. Stretched length. So find out the stretch length is gonna be the total length of the spring minus the original length. And they're going to equal to the kinetic energy. So that is half mv squared plus the potential energy. So the potential energy, like we don't have the potential energy in the spring right now, but we do have some potential energy from the gravity. So like we're gonna have some height over here. And I'm gonna call this one h for now, plus mgh. So next step is just plug in a number. 0, I'm not gonna write it. Only a half. Shouldn't be a plus there. So only like the half. K is 100, is 1500 times x. So the arm is pulled back such that the displacement s is equal to 100 millimeter. So now, like, remember, we need to change the millimeter to meter, so that is 0.1 meter. So here is times 0.1, because like the coefficient is in meter, and here we have the length in millimeter. So like we need to make the unit match. So like we need to convert the length units to the power of 2. It's equal to half m. We know what is the mass, that is 0.3 kilogram. Velocity is the unknown we're looking for, plus 3 times 9.81 times the height. So to find out this height is just gonna be, okay. So it's just gonna be the total height on this one minus the height on this one. So gonna be the purple color, like the purple length minus the blue length. 1.5 meter minus 1.5, that is cosine 60 degree. And this is what h is. So again, just use a calculator. Then we can find out the velocity is equal to 5.94 meter per second. 5.94 meter per second. Okay, so now we have the velocity. We have the velocity when the ball reach this location where the theta is equal to 60 degree. And next one, we're gonna like use the free body diagram on here to find out the reaction force. So next one will be from the free body diagram. So on the free body diagram on here, we know that the resultant force in the normal direction, or the direction that is pointing inwards, pointing towards the center of the circle, is equal to ma. A is the centripetal acceleration, and the force like pointing towards the center is n minus mg cosine theta is equal to m. The centripetal acceleration is equal to v squared over r. So just need to plug in the number again. What's going to be the mass? 0.3 times 9.81 times cosine 60 degree. That is equal to 0.3 times velocity over the radius 1.5. So just solve for the reaction force N, which is equal to 8.53 Newton. Okay, then let's go to the next one. So the next three questions will all gonna be about the what's it called? The conservation of the impulse and momentum. So the equation gonna be for the impulse. Oh, forgot how to spell it. I didn't write it. Anyway. For the momentum is equal to mv, that is mv, and the impulse, I think that's correct, is force times the time of the force. So the conservation of this impulse and momentum will be the momentum at the first moment plus the force plus the impulse at the first moment equal to the momentum at the second moment plus the impulse at the second moment. So that is just the basic equation, principal equation. So let's take a look at this question. So the boy jumps off the flat car at A with a velocity of 4 feet per second relative to the car. So actually this one is important, like the velocity is relative to the car. So this 4 feet per second is relative to the car, but not the ground. And it's gonna land at the second flat car B. So it's gonna jump from the first car towards the second car. And we're going to determine the final velocity, final speed of both cars after the motion. And the mass for each car is 80 pounds. And the mass for the boy is 60 pounds. Okay, and like everything is from the rest at the beginning and neglect the mass of a wheel. So the first moment we're gonna say is the boy just jump out, like it's not landed, it's still like in the sky. It's just like jump out and the car is moving back. So our first scenario is the boy car A is moving backward. Car is moving backwards. Boy is still. So that is the first scenario we're considering. So then we're gonna apply the conservation of impulse and momentum. So the original equation is the momentum at the first moment plus the impulse at the first moment equal to the momentum at the second moment plus the impulse at the second moment. And since everything is like starting from the rest, that means this one is 0 and this one is also 0. Like at the first moment, we don't have any force. And they're going to be equal to the momentum at the second moment and the force at the second moment, impulse at the second moment. And we also don't have the force, like we don't have a force is like applying to anything. So this one also goes to 0. Like the only thing we have is the momentum. So it's gonna be the momentum of the ball that is m b boy vb in the x direction. Like we're only analyzing the horizontal direction, because in the vertical direction, like the car is not gonna like going downward, so like we don't need to consider anything about the horizontal direction now. Plus the mass of the car times the velocity of the car. So here is the first balance we have. Let me see. Oh, and the velocity, like, remember the velocity here is the relative velocity. Between boy and car. So the first equation, we have two unknown. Wait, let me see. Then be 0 equal to this one plus this one plus this one. Okay, so we only have one unknown as the VA. So then we can just plug in a number. That is 0 is equal to MB 60 over 32.2 times VBX. So velocity of the boy in the X direction will be 4 times, so 4 is on here in the in the horizontal direction, it's gonna be the 12 component here. So that is 12 over 13 plus the mass of the car is 80 pounds times the mass of the car. So from here, we can find out the mass of the car, I mean the velocity of the car. And that is equal to negative 1.58 feet per second. Means the car is like moving backwards, which actually makes sense. So now we need to find out the velocity of the boy, like that is relative to the ground. So it's actually an equation about the relative velocity again. Like now what we find is the velocity of the boy relative to the car. A is equal to the velocity of the boy minus the velocity of the car. So velocity of the boy relative to the car in the horizontal direction, that is 4 times 12 over 13 is equal to the velocity of the boy, which is the unknown we're looking for, minus the velocity of the car minus 1.58. So on here, we can find out the velocity of the boy relative to the ground in the x direction is equal to 2.11 feet per second. I'm just gonna change the notation on the top a little bit. Oh wait, that actually never mind. Like in this equation, like when we are using the balance of the impulse and momentum, the velocity we put on here should be the velocity like relative to the ground. Shouldn't be a relative velocity like this one should be the one like on here. And then if we keep going down, so on here, we shouldn't have this equation now for now. So essentially what we have is two equations like this. So that is the balance equation. And then in this balance equation, the velocity of the boy is the velocity that is relative to the ground. But in the question, the velocity on here is the velocity that is relative to the car. So on here, like we only have the velocity relative to the car. So we need another equation, which is the second equation below, to find out what's the velocity that is relative to the ground. So on here we have two equations, and then we have two unknown, that is the VB and VA. VB and VA. So two equations and two unknown. So here is two equations and two unknown. We can solve for BB and BA. Yeah, that makes sense. So now we have the velocity of the car that is actually moving backwards. And then we can continue for our second movement. I guess I will write it over here. So the second scenario is the boy land on car B. And when the boy land on car B, that means the boy gonna have the same velocity as the car B. So at this moment, the boy will have same velocity as car B. So the equation, like the conservation of impulse and momentum equation, will be the momentum plus the impulse at the second moment is equal to the momentum plus the impulse at the third moment. F3T3. And also, like, we're not dealing with the force, so all the force term will be 0. And like we're only dealing with the momentum now. So the mass at the second moment will be the mass of the boy times the velocity of the boy relative to the ground. So going to be this one. And since like the car at this moment is not moving, like car B is not moving, so we don't need to include the car at this moment. Like if we're saying that VB and this VB is the car, which is 0. So like anyway, it's going to be 0. And when the boy actually land on the car, the mass will be the total mass of the boy and the car. So going to be MB plus mass of the boy plus mass of the car. And they're going to have the same velocity, so times VB. So I'll just erase this one. So it will be a very short equation like this. And this one is mass of boy. And this is mass of car B. So that will be 60 over 32.2 times VB, which is 2.11, is equal to 60 over 32.2 plus 80 over 32.2 times the velocity of the car and the boy. So one equation and one unknown. And the velocity of the system, like the velocity of the car and the boy, is equal to 0.904 feet per second. Okay, so that is for this question. So for this question, we just need to consider the entire question as two scenarios. The first one is the boy just jumped up and it's still like flying, it's not landed. So at this moment, the car A is moving backward and the boy is moving frontwards. And then we're just gonna apply the conservation of the momentum and impulse. And another thing is like in this equation, remember all the velocity we're gonna use is relative to the ground. So like we still need to convert the velocity to the global velocity and then plug into the equation. So like that is the first scenario, we find out the velocity of the car and the velocity of the boy that is relative to the ground. And then the second scenario is the boy just like landed on the car. So like when they actually landed, the speed of the boy and the speed of the car are gonna be the same because like he's standing on the car. And then just use the equation again to find out the final velocity. That's it. Okay, so next one. Yeah. So basically you have a guy that is like just jump up and then it's gonna land on the sand. And so those are no relevant information. So actually start from here. Assume that the velocity of an 80 kilogram athlete. So this guy have a mass is 80 kilogram. And the velocity in the air is 9 meters per second with an angle of 35 degrees. And when it landed, it took him 0.2 seconds, 0.22 seconds. That means when we are calculating the impulse, the time is going to be equal to 0.22. And determine the horizontal impulse force on his feet during the landing. So the same thing, we're gonna apply the conservation of the momentum and the impulse. T2. Okay, so in this equation, the first moment, like on the left-hand side is when the guy just like still flying, it's not landed. So at this moment, it doesn't have any force. So the impulse term gonna be 0. And after he landed, like since he's just like sitting in the sand, the velocity gonna become 0. So we have like 2 terms eliminated. So the equation gonna become more simple to something like this. So like next one, we are just going to plug in the value for the mass is gonna be equal to 80 times the velocity, that is 9 meters per second, but the 9 meters per second is like pointing downwards. And now we're only finding the velocity in the, like we're only calculating the momentum and impulse in the horizontal direction. So we just need to times cosine 35 degrees to find out the velocity in the horizontal direction. This one is the and that is equal to the force, the impulsive force times the time. And now we know that time is equal to 0.22. So F2 is equal to 2.86 kilonewton. Like for this one, the question looks very long, but actually it's very easy. Okay, so the last one, oops. So we have another box is in the stationary, like that means the box is not moving at the beginning, which is 20 kilogram. And the force, like the magnitude of the force is actually a function of time, like is on here. So on this block, we know that the function, I mean the time function is, the force function is equal to P equal to 50 T. So that is just a function of this, this line. And we're going to determine the time Ts when the block come rest. So in the first 3 seconds, the pulling force is going to be increase until 150. I guess that's Newton. Yeah, it's Newton. So it's going to be increasing from 0 to 150. And then after 3 seconds, there's going to be no force. And since there's going to be some friction, and so the block or the box on here is going to eventually stop. So when we just apply the force on the blocks, on the box is not gonna move. Like when the force, like you can imagine when the force is like too weak, it's not like good enough to pull up the box. So first we need to calculate like at what time the box is actually gonna move. So that is gonna be our first step is calculate when will the box move. And on here, like we have 2 frictional coefficient. So the one on the bottom is the static one. That means when the box is like it's not moving, we are going to use this friction coefficient. So like we know the friction, the maximum friction is equal to mu s times mg F max at the stationary condition. So that is equal to 0.6 times 20 times kilogram, 9.81, which is equal to 117.72 Newton. So that means we need 117.70 Newton to actually move this box. So now we can calculate like at what moment we can actually arrive this force, this amount of force. So from the graph is, we know like the pulling force P is equal to 50 times T, and T will be equal to P over 50. And now we want the P is equal to the maximum friction, 117.72 over 50. So that gives us T naught is equal to 2.344 seconds. Okay. So like from here, we know that the box is not going to move until 2.344 seconds. So after this second, the box is going to move. So the next one, we're just going to calculate. Okay. Yeah, so the next one is just going to calculate T time T. And we're also going to apply the conservation of momentum and impulse. I'm keep forgetting the name of like the impulse. So calculate same thing, V1, M1 V1 plus F1 T1 equal to the momentum and the force and the impulse. So at the final moment, like we know the velocity is 0, so that is going to be 0. And also at the first moment, that is like when the box just about to move. So at that moment, the velocity is still going to be 0. So we have 2 0 here. Like the first one is when the box just about to move. Actually, I'm going to write it down. Velocity is still equal to 0. And the last one is the box stopped. In this case, velocity is also equal to 0. So the only thing left is F1 T1 is equal to F2 T2. So let's do the right-hand side first, it's easier. So for the right-hand side, the force is gonna be the friction, like the friction is always like applying to the whole system. So that is the kinetic friction coefficient times the weight or the gravity of this box times the time, t minus t0. And the first one, like this one, we're going to use the integration again. Because like on here, like we notice that it's like actually it's like a function of time. So from here, we're just going to build up a integration. That is, we're integrating from the box moving until like we know there's no force like applied to the box. So from 2.345 seconds to 3 seconds. And then it's 50 dt. Yeah, that's it. So just solving this equation, 0.4 times 20 times 9.81 times t minus 2.345. On the left hand side, doing the integration of this one will be 50 times half t squared, evaluating from 2.345 to 3 seconds. So on the right hand side, on the left hand side, it's going to be 25 times 9 minus 2.345 to the power of 2 is equal to 8 times 9.81 times t minus 2.345. So now like eventually you're gonna have time is equal to 3.46 seconds. Yeah.
Why did you do t minus t9?
Like on the integration here,
Yeah, on the right side.
because we are already like have the t. So like, if we like, we can just like forget about the integration now. Like we're just going back on here. So what integration do is like we're just finding the area of this part, right? And like at this point is 2 point what? Like 2 point something 35. So like eventually what we do is just finding the area of this, finding like what's going to be area of this shape. And this shape is f times t, that is the impulse. So like the whole idea about the left-hand side of the equation is just like finding the area of this one. And the area of this one is going to be equal to area on the right-hand side. Okay, so first I'm gonna stop the recording. Where did I record it?